A-level mechanics, circular motion. We're going to consider a particle moving in a circle at a constant angular speed. So let's have a look at circular motion. Often objects move in a circular path. The Earth moves around the Sun in a circular orbit, as does the Moon around the Earth. A stone in a sling is spun around until it's released. An object on a turntable rotates about the axis of the turntable. In this video we'll explore the causes and effects of circular motion. But while studying circular motion, angles will almost exclusively be measured in radians. Let's just remember, if we measure a unit length around the circumference of a circle with unit radius, then the angle subtended at the centre of the circle is 1 radian. 1 radian is approximately equal to 57.3 degrees. In fact, 180 degrees is exactly equal to pi radians. The reason for doing this is we're going to use calculus quite a lot, and to differentiate we need to have all angles measured in radians. Let's have a look at angular velocity and acceleration. If an object is rotated through theta radians, at time t, the angular velocity is d theta by dt. This is often written as omega. We also often use Newton's notation for differentiation. That is, to differentiate with respect to time t, we write a dot over the letter. So theta dot is d theta by dt, and theta double dot is d2 theta by dt squared. So theta double dot is the second differential of theta. And we have omega is equal to theta dot. Now the angular acceleration is often written as alpha. So alpha is equal to theta double dot. Now the angular velocity or angular speed, as we've said, is usually measured in radians per second. But it can be measured in revolutions per minute, known as RPM. For example, a record player can turn at 78 RPM, 45 RPM, or 33 1/3 RPM. A car engine turns at an angular speed between 600 revolutions per minute and 8,000 revolutions per minute. Now 1 revolution is 2 pi radians, so 1 revolution per minute is 2 pi divided by 60 radians per second. Let's consider motion with constant angular velocity. Consider a particle moving at constant angular speed of omega around a circle radius r. Then if it rotates an angle theta, it'll have moved a distance r theta. So we can say the distance travelled s is given by s equals r theta. And if we differentiate, because r is a constant, we get ds by dt equals r d theta by dt, or s dot is equal to r theta dot. So its speed v, which is s dot, is given by v equals r omega. If we differentiate again, since r and omega are constants, we get dv by dt is equal to 0. This means the acceleration in the direction of the speed v is 0. That is, the tangential acceleration is 0. However, the direction of the speed v is constantly changing, so the vector v is not constant, and there is acceleration. Consider a particle on the ij plane, starting on the x-axis and moving at a constant angular speed of omega around a circle, centre O, and radius r. Let the position at time t be s. Then x is equal to r cos omega t, and y is equal to r sin omega t. So s is equal to r cos omega t I plus r sin omega t j. But because omega, I, and j are all constants, differentiating we get, starting with s equals r cos omega t I plus r sin omega t j, And the differential of cos omega t is minus omega sine omega t. The differential of sine omega t is omega cos omega t. This gives us the differential s dot is equal to minus r omega sine omega t I plus r omega cos omega t j. And differentiating again, we get s double dot is equal to minus r omega squared cos omega t I minus r omega squared sine omega t j. Now we can factorise that by taking minus omega squared out as a constant term. And we can see that what that gives us is s double dot is equal to minus omega squared s. And if we take the modulus of each side, now the modulus of s double dot is a, and the modulus of s is r. So this gives us a is equal to r omega squared, where a is towards the centre of the circle. So the particle has an acceleration towards the centre of the circle of r omega squared. But we've had that v is equal to r omega, so we can get omega is equal to v over r. And from a equals r omega squared, we've got a is equal to r into v over r all squared, which simplifies to a equals v squared over r. So the acceleration of the particle is r omega squared, or v squared over r, towards the centre of the circle. Now that's an important result. Let's quickly review what we know about circular motion with constant angular velocity. Now we're considering an object which is moving in a circle, radius r, with constant angular speed omega. Now if the angle rotated is theta, then omega is equal to the differential of theta, theta dot, and theta is equal to omega t. Now the distance travelled is r theta, which is equal to r omega t, and the speed is in the direction of the tangent, which is equal to v, and v is equal to r omega. The acceleration is towards the centre of the circle, and that's r omega squared, or v squared over r. Let's look at an example. Example 1. We're told a body of mass 0.25 kilograms rests on a horizontal turntable 12 centimetres from the axis of rotation. The turntable turns at a speed of 45 revolutions per minute, but the body does not slide. Calculate the frictional force acting on the body. Well, to solve this, we need to draw a diagram of the side view and mark in the forces. Now there's the weight of the body, which is 0.25 g, where g is 9.8. There's a normal reaction vertically up, and there's a frictional force F towards the centre of the turntable. So if we resolve horizontally using F equals ma, we have the acceleration is equal to r omega squared. So F is equal to mr omega squared. Now omega is 45 revolutions per minute, where 1 revolution is 2 pi radians. So that is 45 times 2 pi radians per minute, or 45 times 2 pi over 60 radians per second. And that works out to be 4.712388. So the frictional force mr omega squared is equal to 0.25 times 0.12 times 4.712388 squared, which is 0.66198. So the frictional force rounded off is 0.662 newtons. In example 2, we're told the mass of the moon is 7.432 times 10 to the 22 kilograms. The distance from the Earth to the moon is 384,400 kilometres, and the moon orbits the Earth in 27.3 days. Find the force of attraction between the Earth and the moon. Well, to solve this, we can use F equals ma and a equals omega squared r. So F equals mr omega squared. Now the Moon orbits the Earth once every 27.3 days. So it makes one revolution, which is 2 pi radians, in 27.3 days, which is 27.3 times 24 times 60 times 60 seconds. So omega works out to be 2.6638 times 10 to the minus 6 radians per second. Now the mass of the Moon is 7.432 times 10 to the 22 kilograms, and the radius of the orbit of the Moon is 3.844 times 10 to the 8 meters. So, substituting into the equation F equals mr omega squared, we have F equals 7.432 times 10 to the 22 times 3.844 times 10 to the 8 times 2.6638 times 10 to the minus 6 all squared, which works out to be 2.0272 times 10 to the 20. And so the force is 2.027 times 10 to the 20 newtons. In example 3, we're told a conical pendulum consists of a light string of length 40 centimeters fixed at one end, with a particle of mass m attached to the other. The particle moves in a horizontal circle, with the string making an angle of 30 degrees with the vertical. Find the time taken to make one revolution. Well, to solve this, we first need to draw a diagram and then mark in the forces. First, there's the weight of the particle acting vertically down, and that is mg, where g is 9.8. And then there's the tension in the string. If we resolve vertically, the vertical component of t is t times the cosine of the angle between t and the vertical. So t cosine 30 is equal to mg. In other words, t is equal to mg over cos 30. If we resolve horizontally using F equals ma, then the horizontal component of t is t times the cosine of the angle between t and the horizontal. That's cosine of 60 degrees. So t cos 60 degrees is equal to ma. But we know that the cosine of 60 is a half, and a is equal to r omega squared. So t times a half is equal to mr omega squared. Now, if we look at the triangle ABC, we see that r is equal to 0.4 sine 30. And we know sine of 30 is a half. So that gives us t times a half equals m times 0.4 times a half times omega squared. And that simplifies to t equals 0.4 m omega squared. Now, if we substitute t from equation 1, we get mg over cosine 30 equals 0.4 m omega squared. And the m's cancel. We can divide both sides by 0.4, so that gives us omega squared equals g over 0.4 cosine 30, or 9.8 over 0.4 cosine 30. And that works out to be 28.2901. So omega is the square root of that, which is 5.3188. Now in radians, one revolution is 2 pi. So the time taken is the angular distance divided by the angular speed, that's 2 pi over omega, which is equal to 2 pi over 5.3188, or 1.1813. And so the time taken for one revolution is 1.18 seconds. In example 4, a light string of length 11 meters is attached at each end to points A and B, with A 8 meters vertically above B. They're connected in such a way that the strings can swivel freely around AB. The string passes through a smooth ring of mass 200 grams, which can slide freely along the string. The ring C is projected horizontally around AB so that it performs horizontal circles with AC equal to 7 meters. In the first part, we're asked to find the tension in the string. Now to solve this, on the diagram, we first mark in the forces. Now the weight of the ring acts vertically downwards, and that is 0.2 G, where G is 9.8. Also, since the ring is smooth, the tension is constant along the string. So we can mark in the tension acting on the ring as T. Now we can work out the angles at A and B. So using the cosine formula, we get the angle A is equal to the inverse cosine of b squared plus c squared minus a squared all over 2bc, where a is 4, b is 7 and c is 8. So that gives us a is equal to the inverse cosine of 7 squared plus 8 squared minus 4 squared over 2 times 7 times 8, and that works out as 29.99473 degrees. And similarly, b works out as the inverse cosine of 8 squared plus 4 squared minus 7 squared all over 2 times 8 times 4, which equals 61.02847 degrees. So, going back to our diagram, we can resolve vertically on the ring. We have the angles between T and the vertical are A and B. So, this gives us T cosine A equals T cosine B plus 0.2 G. Now we can write that as T cosine A minus cosine B is equal to 1.96. So, T is equal to 1.96 divided by cosine A minus cosine B, which is 1.96 over 0.381696, which is 5.13497. So our answer is the tension T is 5.13 newtons. In part 2, we're asked to find the angular speed of the ring. Now, if we resolve horizontally, we have T sine A plus T sine B is equal to m omega squared r. Now, from triangle ACD, we have r is equal to 7 cosine A, which is 3.4994. So, substituting in the equation above, we have 5.13497 times 0.49992 plus 0.87486 equals 0.2 omega squared times 3.49944. Well, this can be rearranged as omega squared is equal to 5.13497 times 1.37478, all divided by 0.2 times 3.49933, which works out to be 10.086. So omega is equal to the square root of 10.086, which is 3.1759. And so we have the angular speed omega is equal to 3.18 radians per second.